evening and welcome to Tinkering with Edkelar. This time I got something special. Not a restoration or refurbishment, but rather a low-level recreation experiment. I am not a gamer kitty, nope. While I enjoy a few levels of Doom every now and then, most of today's games are way too difficult for casual playing. That said, I do realize what an awesome history video games have. And to have a bit of retro fun, I decided to make myself a Pong console. Clearly, there are many clones out there. For a time, almost every game was a Pong derivative, and programming something like it with the CPU is almost a beginner exercise. Original PCBs would be way too expensive, so after a bit of digging on the internet, some blurry schematics were uncovered. I decided to go with the original design as closely as possible and make myself a PCB for it. As a starting point, I copied the slightly jumbled schematic to KiCAD, making generous use of the hierarchical schematics, grouping the content according to the blocks labeled on the original. The quality of the scans is on the low end. I had to make educated guesses on some of the connections. This means that my first version will most likely have some errors in it. It took days of shuffling logic gates around and labeling nets for cross-sheet connections, but eventually I think I got it all connected. Next step, making a PCB. Oof, that is also going to take some time. My first attempt ended in a design that had the ICs way too close together, so I ran out of space for the tangle that is required to be connected. Take 2. Keeping more space between the ICs. Initially, I tried to keep them together according to their functional blocks, but that proved futile since some gates were stretched across multiple blocks. So the only 3 blocks that are still somewhat together is the clock generator and the timing blocks. The rest is divided up one chip after another, based on the shortest connection for each. An expert might tease out some optimizations, I'm sure about that, but I dare say I like the result. A quick note on PCB routing. Just in case it's a new topic for you, I picked a dual layer board as I thought the original might also not have had any internal layers, and one layer would need way too many bridge wires. To keep sane, it's a good idea to use one layer for vertical and the other one for horizontal traces. That way you can always use vias to jump over existing traces. I followed that rule only after the timing section was almost finished and had to rework a bit of it. Next step, exporting the design files and ordering a prototype PCB. And while I wait for it to arrive, it's a good time to look at the circuit. Don't worry, I'll not go into detail of every single gate, even though in this case I could. Let's start off with the clock and timing section. For a clock source, we have a 14.31818 MHz crystal. It is also put into a typical inverter-based oscillator, buffered via another gate and put through a JK flip-flop to divide it by 2. This means the actual clock signal is running at 7.15909 MHz. Conveniently, that flip-flop also provides an inverted clock signal, which will become important later. The timing section is made up of 2 distinct blocks, originally labeled horizontal and vertical sync. The horizontal section takes the clock input and derives a set of frequencies, labeled H1 for the fastest and H256 for the slowest, which come out at 3.579545 MHz and 13.982598 kHz respectively. These clocks are fed into a comparison circuit to reset the counters once they reach a target value, giving us a signal with 15.768921 kHz. This is close enough to the line frequency of NTSC, and based on another set of comparisons, we get the matching horizontal blanking and sync pulses. The second block is the vertical one. It takes the horizontal reset as an input for its counter section, thus counting the line numbers in the upcoming TV signal. Like the horizontal, the vertical has V1 to V256 signals with 7.8844605 kHz and 30.798674 Hz respectively. The comparison in this case resets the counter at 60.417322 Hz, close enough for the NTSC vertical sync. Let's move on to the video mixer, since that might be the interesting next part. It takes the horizontal and vertical sync pulses from the timing section and combines them into a sync signal. This is then inverted, since NTSC sync pulses are active low, and a resistor network creates an output voltage by combining them with other inputs. Since I was not quite sure about the absolute voltages here, I added a trimmer to the output, but in general, the video mixer is a simple 3-bit input resistor-based digital to analog converter, with the other inputs coming from the score digits, which are the lower levels of white, and whatever else might be visible at any moment, the ball, pedals, or the net. The ball itself just buzzes around the screen all the time. The movement is controlled horizontally with this circuit. Every hit, triggered by the hit sound enabled line, counts up a counter that defines the speed, so the ball should accelerate the more often it is passed between the players. The circuit also keeps track of the direction the ball is moving, left or right, based by some other inputs, either a hit on a pedal or the ball is going off screen. The speed output feeds into the horizontal position circuit. Here we have 2 counters that give a signal once the ball is in the current horizontal pixel position. These are reset if the game is waiting to serve the next ball. The vertical ball speed is a bit more elaborate. The speed here is set with a bit of logic and a 3-bit input. I'll get into that in a moment. Other than that, it is also just a counter output for the vertical ball position circuit. Same as the horizontal one, we get an output here if the current line holds the ball. And these 2 positions give us, we need to draw a pixel for the ball. Yay! The next block in the grand scheme of things is the game control one. Here we have the coin switch input. It is using a rather brutal debouncing circuit that triggers a score reset signal, i.e. a start new game signal. The weird analog part next to it is a head scratcher, until you read up a bit on the history of Pong revisions. Apparently they had an issue when you click the piezo lighter next to the game and it would give you a free game, obviously triggering a score reset in the circuit with an EMP. Instead of fixing that, Atari decided to make an amplifier circuit that detects EMPs and triggers a reset instead. The other components here make sure that the game is stopped if one of the players reaches the target score. This condition will put the game into attract mode. This block over here combines the "is this a ball pixel" signal and the "is this a pedal pixel" signal, and if both are set, we have hit the ball. Yay! Last but not least, this section on top triggers a new round by serving the ball. The initial offset is somewhat randomized based on pedal 1 position as an input and a 555 timer for a slight delay. The pedals are a bit easier again. The potentiometers for input derive a voltage that is fed into another 555 timer. It gets reset at every frame and sets the output after a proportional delay. This then starts a counter for a set number of lines. The result is the "is the pad in the current line" signal and a set of bits that indicate the position within the pad. These are used to derive the vertical ball speed upon hit, and that makes the ball jump off at a different angle depending on where on the pad you hit it. The little section on the bottom edge is adding the horizontal information to give the "this pixel is part of pad 1 or 2" information. Note that attract mode will always make the pedals disappear here. The score counter is simple enough. If the ball is a miss, the direction of the ball dictates which of the two players gets a score added. Based on the decoded output of the counters and the switch on the PCB, we also set the stop game signals. I'll come to the missed ball detection part a bit later. The score decoder takes the scores as an input and, based on the current screen position, feeds that score into a 7-segment decoder chip. It will have the segments to match the current score digit on screen as an output and be blanked when there is no digit at the current pixel position. The score display takes these segments and converts them into a show score pixel information for the video mixer based on the horizontal and vertical counters. And we are almost done. The net generation is a very simple one indeed. It creates an alternating dash pattern in the center of the screen based on the original clock for the pixel widths. And last but not least, the beeps and boops. The sound is delivered by combining the appropriate signals like hit and ball out horizontally or vertically with either the 1000 or 500 Hz signals from the timing generator. And that sound signal is then fed to the output, but only if the game is currently running. Attract mode is quiet. Like with the video output, I added a pot to trim the levels on the output. In the meantime, the PCBs have arrived. Aren't they a work of art? So up next, lots of soldering for revision A. I'm putting in the chips according to their function blocks, so I can test one section after the other. I think it's easier to narrow down bugs this way. The clock generator is the first that goes in, and it immediately works. Next is the horizontal timing section. It also looks promising. The vertical timing is the next part, close to 60 Hz. Yes! Now to the video mixer. The output does look like an NTSC signal, but my TV won't detect it. So something's off. To check if my TV is just mocking me, I put in the net generator next, since it's the easiest part to get pixels to show up. But still, nothing. After a bit of troubleshooting and comparing the digital to analog converter output levels with an NTSC reference signal, I finally discovered that my circuit diagram was a bit noisy. I misread a 2.2 kilo ohm resistor for 22 kilo ohms. That gave the sync signals the wrong levels when compared to the other parts. After changing that, my TV got signal. Ta-da! I got a net on the screen. Moving to the pedal circuits. And I can see something. But not every time. Turns out that I messed up on this core detector. The 11-15 point switch should be open on one side, and I dutifully connected these to ground. But they need to go to VCC to work. Whoops! Also, the pedal position detection won't work at all if the input is grounded. My prototype had the unplugged pedal grounded, so the pedal wouldn't show up if the plug wasn't in. Moving on again, the ball movement is tied to the game control and thus amongst the more complicated parts. But eventually I got it. Well, sorta. There is a distinct lack of horizontal movement. And again, tricked by my own devices. The aforementioned pedal won't show up if unplugged issue bit me again. Remember that the serving logic uses pad 1 position as randomized input? Well, if pad 1 isn't showing, then the ball isn't released. Humph! After trying to hit the darn ball, I eventually gave up. Something was off. I clearly hit the ball several times, but it passed right through the pedal. This time there was a real issue with my circuit. I misread the hit 1 and hit 2 inputs on the direction flip-flop. So instead of turning the ball around, I just confirmed the direction it was going in. Whoops! I needed to flip the signals on that chip. The first true botch, but now I can hit the ball. The sound generator is up next. And we got beeps and boops. Yay! The weird bars all over are caused by the score display, which is now somewhat connected too, but does not get the right input yet. So let's populate that. And here's a problem. The 7-segment decoder is a 74LS48, which is not available new anymore. Other versions exist, but won't work in this configuration. Almost all of the new ones are open collector types. This one needs to put the output pins low when a blanking is requested, so without any changes, only the 7448 will work. I found one on eBay, but delivery was a bit slow. In the meantime, I used the 7447, which is the same but open collector, which means the blanking won't work. And yes, it does look like it. With all of these phantom segments around, it's hard to tell if the score is counting right. And after receiving and putting in the correct chip, woohoo! Score display! Well, sorta. The top segment is rendering in the same position as the upper left one. Which brings me to my second circuit mistake, the decoding logic for that segment pixel. I accidentally used V instead of H signals for that top digit, so it was flipped by 90 degrees. Whoops! Ignoring that wonky segment for now, there is also a scoring issue. When the ball leaves to the left, the right player gets a point, the buzzer goes off, and the game serves the next ball. All fine. But when the ball goes off to the right, the buzzer goes off and the game serves the next ball. No score for the left player. This needs investigation. I tried to narrow down the issue with the HP logic probe, then extended my research to the logic analyzer, but in both cases it seemed that the miss signal was not triggering in case the ball was moving left. Only when the ball was going right it triggered. Which is weird, because the miss signal feeds all the other stages: score, buzzer and serve trigger. I got a hint of what was going on when I tried the logic probe and my scope again. As soon as I tried to measure the hit signal, it wouldn't trigger the sound anymore too. Only the serving logic. Aha! A clue! And here's the solution. A timing glitch. I'm pretty sure the original had that too, but the older ICs might have hidden that fact. Modern ones are quite a bit faster in their switching times, and this is where the issue comes in. You see, the miss signal is created by combining the horizontal blanking signal and the ball signal, so as soon as the ball goes off screen horizontally, that signal goes active, low that is, and if the game is running, i.e. not in attract mode, it also signals a missed in-game to the counters. The miss signal is also used to trigger the missed sound 555 timer and to set the surf signal. The surf signal in turn resets the horizontal ball position, and with the ball position reset, naturally, the ball is no longer off screen, so the miss signal is clearing itself as soon as possible. Too soon in some cases. Even adding the capacity of the probes caused the 555 trigger to fail, and the score trigger, which is beyond 3 more gates, didn't even have a chance. Now I don't really know why there was a left-right difference, but at any rate, the miss signal needs a latch of sorts. Unused gates to the rescue! I added a D flip-flop to the missed signal and clocked it with the inverted clock signal. That way, the output will be delayed by a clock cycle and everything has a good chance to propagate. And while the botch looks a bit far out, it does work. Woo! Scoring in both directions. And while I wait for the final PCB update to be delivered, I am starting to make a case for it. My idea is to have the PCB on display inside, so a clear cover is a must. The front needs cutouts for the score switch and pedal connectors with their trim pots, as well as the coin button. I think another revision might put that on the PCB too, but I thought I might want to connect an actual coin slot. Maybe not this time. The rear needs two cutouts for the AV sockets and the power input, and a rather toasty heatsink for the 7805. To keep a touch of 70s flair, I opted for wooden side panels with a sheet metal bottom, front and back. Should look pretty slick. Putting some stain and finishing on the wooden parts. For the pedals, I opted for project boxes. These will be handled, so wood or transparent will become grimy pretty quick. Better use regular plastic for those. Ah, the pedals. I almost forgot. The original shows them as potentiometers between VCC and ground, but that didn't have a proper result at all. They would disappear from screen on top and would also wrap around on the bottom side. The trimmer would only get them in line ever so much. I checked up on them, and to have a reasonable range, the input voltage needs to be between 1.3 volts and 4.3 volts apparently. I decided to put in some diodes on the potentiometer inputs to shift that range. And after some cutting, drilling and bending, I can finally assemble that thing. And here we are, my pedal game. It works. Note that the picture seems to be shifted to the left and you can clearly see some artifacts of the ball on the right. I bet these were originally compensated by adjusting the horizontal position and size in the cabinet's TV. But hey, it works. And this concludes this rather elaborate project. While I am pretty sure that I'm not giving away any trade secrets in a 50-year-old circuit that is readily available online for ages, I am quite sure that I cannot publish this version just like that. If somebody with more knowledge on the subject can provide input and I can publish it, I'll upload it to my GitHub repo. And that's it for this episode. I hope you enjoyed it. See you next time! Remember that the serving logic uses